All right. So, a very good morning. What we are going to do today is initially for about few minutes we are going to discuss some useful properties of DTFT and then move on to the practical part of one of the most practical implementations of Fourier transform, which is the DFT. Now, of course, what I should also tell you is that I am only giving you an overview. In about I think about 5 to 6 lectures we have kind of covered the most important aspects of Fourier transform, theoretical aspects, but there is a lot more, and obviously this course is not equipped to, or we do not have the time to go into detail, but this entire subject of Fourier transforms is an ocean in itself, and if there are various applications and then there have been various modifications and variations and so on. There is something called discrete cosine transform and different kinds of Fourier transforms that have actually taken birth after this, but we are only discussing the most relevant ones. I strongly recommend you go and actually read some literature, also not just for learning but for also appreciating. I remember seeing an article in Siam journal which talks about how our human ears are kind of implementing the Fourier transforms, because if you look at the beauty of the auditory system, it is able to distinguish between several sounds occurring at the same time. And if you look at the signal characterization of auditory signals and so on, you would see that there are many frequencies, different frequency content. So, if you were to stand outside on a road, you would hear the sounds of the traffic, the sounds of maybe dogs barking and humans speaking, and so many different sounds. They all belong to different frequency regimes. I mean, they have different frequency content. It is amazing that our human ear is able to really distinguish all of this for us and be able to say, yes, there are these different sounds occurring out there. Not only standing on a road, when you are listening to a song, there are singers and then there is orchestra and so on. And it just does not take Fourier transform alone to explain those phenomena. You will need more advanced transforms like time frequency analysis, transforms used in time frequency analysis like wavelet transforms and so on, which are able to explain how frequencies change with time. But by and large, even if you look at the description of our hearing ability, it is given in terms of frequency, right. Do we know what is the audible range for us, for human beings? 20 to 20 kilohertz, and dogs, for example, can hear lower than 20 hertz, right, and even elephants, for example. So, the different species have been equipped with different kind of filtering characteristics and so on, right, and the G of f that we talked about. So, there is a lot of beautiful things out there. Just read those applications. I mean, it is not just for learning the theory, but for seeing how you can explain several phenomena using this kind of framework like Fourier framework and so on. Therefore, do not think that frequency domain analysis is a very alien field or an alien subject, that I do not see things happening in frequency, I only see things happening in time. Therefore, I am more comfortable with time domain analysis, is what many people say. But let me tell you that what you see is not what necessarily is what you want to believe in, and there are so many things happening behind, and these tools help us understand what is happening behind the scenes. Okay. So, with those words, let me now get started on the properties of DTFT, which are quite useful not only once again in the analysis of signals, but also in analysis of systems. The first in order is the linearity property. It is a very useful property. It says that the DTFT of the sum of two signals, the superposition, is the superposition of the respective DTFTs, which is a kind of a straightforward thing to prove, and we use this as you know very extensively when you are looking at mixture of signals. And the next property, which is very useful, is that of time shifting. Now, all these are, remember, based on this theoretical DTFT, that is the DTFT that we are talking about. So, it says that if a signal has a Fourier transform x of omega, then its shifted version is simply the Fourier transform of the original signal multiplied by e to the minus j 2 pi f d. What it tells us is that only the phase of the shifted signal is altered, right. If I look at the magnitude of the Fourier transform of the shifted signal, so let us say x1 k is the original signal, the delayed signal is x2, that which is nothing but x1 k minus d. Then from the given expression, it is kind of obvious, if I denote x2 k, x1 k minus d by x2 k, it is kind of obvious that the magnitudes of the Fourier transforms of the shifted and the original signals are identical. By the way, I should tell you that the small f that we have been using has different units from that of the big F. Are you aware of that? What are the units of small f? Hertz is a very generic thing, just do not go by hertz. Cycles, that is it? Not bicycles. No, cycles per? No. Go back, that is why I asked you this question, I am sure many of you are not familiar with it. So, compare these two signals, this is a discrete time sine wave and here is a continuous time sine wave, right. So, now can you be correct in specifying the units of small f? Cycles per sample, very, very important, right. Whereas big F has the units of cycles per unit time, if you whatever time, if time is seconds and so on. Both are called hertz, please keep that in mind. Hertz is a very generic name, it is even used for car rentals, but it is as generic as that. So, simply do not say hertz. For example, hertz is used also for specifying sampling frequencies. You know what a sampling frequency is, that is how fast you are sampling, for example, a continuous time signal to produce a discrete time signal, all right. So, just saying hertz is not enough, you have to have an accurate understanding of the units of f. So, this has a units of cycles per sample, whereas the big F has the units of cycles per unit time, right. Both are continuous valued, there is no confusion with respect to that. And of course, you know the difference that this sine wave is not necessarily periodic unless f can be expressed as a rational number, right. If you are able to express f as some m over n, where m and n are co-primes, then n happens to be the period of the discrete time sine wave, whereas the continuous time sinusoid does not have any of these restrictions. Why is that? Because the period of a continuous time signal is on the real number, on the real axis, right, it belongs to the real number set, whereas the period of a discrete time sine wave belongs to the whole number set, well, natural number set I should say, that means positive integers. Therefore, not all discrete time sinusoids are necessarily periodic, you should keep telling yourself that until you know by heart. Okay. So, what we observe here is that the magnitude of the delayed signal is the same as the magnitude of the original version, which means the energy densities would also be identical. In other words, using this is what exactly I meant yesterday and maybe a lecture before as well, that the spectral density plots do not allow us to figure out when a particular frequency existed in over a time interval. That is a consequence of this property here, that is the energy spectral density is blind to time shifts, which is both good and bad. We will not discuss the good part of it and so on, or not even the bad part in detail, but I am just telling you that it has both its merits and demerits. On the other hand, the phase of x2 f, right, the phase of x2 f differs from the phase of x1f by how much? Two pi? Very good. So, it differs by 2 pi fd. Typically, I mean if you assume d to be a positive quantity, then that is the phase difference between the delayed version of the original signal. In fact, this relation is used extensively in estimating delays. So, what you do is I take as I said in radar signal processing, I would like to know, for example, how far the object is, right, or in input output systems, in many systems I want to know the delay between the input and output. So, imagine that x1 is the input and x2 is the output of a system. Then all I need to do is look at the phase difference between the input and output, and of course, I can just use a single sine wave of some known frequency, and then since I know f, since I know the phase of x2 which is output and or the phase difference you can say, I know f, and therefore, from there I can figure out what is d, the delay. This is the standard and a very well known way of estimating delays in not only engineering systems, but any input output system that is linear and time invariant. You can find numerous variants of this method. So, this is a very important and useful property in the analysis of linear systems. And likewise, the dual of this statement. The nice thing about the properties of this Fourier transform is that there is always a dual. What we mean by dual is, just now we talked about time shifts, and we said that results in the multiplication by e to the minus j 2 pi ft. You can also ask this question, if I were to shift the frequency of x of f. What do we mean by shift? Imagine that your x1 of f, I am just going to plot the magnitude. Let us say for some signal it looks like this, okay, and it has some center frequency fc. What we mean by shifting the frequencies, you are going to shift this entire x1 of f, magnitude of x1 of f by a certain amount in frequency domain, right, essentially shifting the center frequency to something else. So, when you do that, and when do you have to do that? In many in all communications and signal, basically when you are communicating signals, this is a standard thing. What happens is, when we are speaking over the phone or when a signal is being transmitted, let us take the human signal, it does not have enough strength at that frequency to be carried over long distances. So, what is done in communications is, this signal that we speak is actually wrapped in a high frequency carrier signal, as you call messenger signal. It is like the postman. So, the postman has the ability to carry your message. So, what is done is, there is a shift of frequency of whatever speech signal that has to be transmitted, and then of course, at the receiving end you will kind of de-shift, you can say. That is essentially the essential principle in communications, where you wrap the the main message in a messenger signal which is of higher frequency. Why do we want to wrap the message into a high frequency signal? Because the losses that occur at high frequencies are lower compared to this low frequency signal, right. That is, if I speak, for example, my speech signal has the ability to reach maybe the last bench or maybe a bit, that is all. It dies its death because there is loss. Whereas, when I am speaking over the phone, it can actually travel thousands of kilometers, right. So, how is that happening? That is because of this wrapping of the message signal. And that is also true in teaching. If you take the raw subject, a raw concept, it becomes very difficult to understand in its raw form. When it is wrapped in a certain context, or when it is explained in terms with a story wrapped around it, then it becomes easy for the student to understand. The only point is, you should not confuse the story for the message. You should be able to unwrap and say, that is a wrapper, the actual chocolate or the concept is inside. That is what is done in communication devices as well. There is a coding happening at the transmitting device, and then there is a decoding happening at the receiving end, and there are some industry standards for that and so on. So, here we are saying that a shift in frequency corresponds to what we call as modulation in time. When you can see this duality here. When we shifted the signal in time, it amounted to multiplication of the Fourier transform by e to the minus j 2 pi f t. Now, when we are looking at shifts in frequency, then it amounts to multiplying the time domain signal by e to the j. What do you see there? 2 pi f k, right? Your f1k, whatever that you are shifting by. So, there is a similarity, and you will see this kind of a duality in almost all the properties of Fourier transforms, and that makes it easy to remember. If you remember how the Fourier transform changes when you perform an operation in time, you should be able to then remember what happens to the time domain signal when you operate in frequency domain. That is the beauty of this. So, for example, here time reversal, that is what we mean by time reversal is you want to flip the signal. That is what we mean by time reversal. You are just going to mirror the signal, and that amounts to actually taking the conjugate. If you can see there, x of minus k results in x of minus f, but that is nothing but x star of f, right. How do you prove that? It is very simple. X of f is sigma x k e to the minus j 2 pi f k, and x of minus f is therefore sigma x k e to the j 2 pi f k, which is nothing but the conjugate of this. Okay. So, flipping the signal in time amounts to taking a conjugate in frequency domain, and likewise you can see here, flipping in frequency amounts to actually flipping the time domain signal. So, the dual is contained in the statement. Now, this is the scaling property. The fourth one that we are looking at is a scaling property, which is not so useful in this course. It is a lot more useful in time frequency analysis. What this property says is, if I have a signal in time whose Fourier transform, let us say, is x of omega or x of f, when I scale it, and here we are not talking of amplitude scaling, you should not confuse this scaling with amplitude scaling. When what I am looking at here is scaling in time. So, you are actually shrinking or dilating the time axis. If you look at it carefully, you are saying x of k by s. It says that the Fourier transform accordingly is dilated or compressed. For example, you take x of k over s. The property says that the Fourier transform of x of k over s is x of sf. So, the reverse is happening in the frequency domain. Let me ask you a simple question here now. If I have x of k whose Fourier transform is x of f, let us say, all right. I have used a big F, I will correct that. And now we are looking at the Fourier transform of the scaled signal, and here scaling is in time. So, let me ask you a question now. If s is some scaling parameter, suppose s is 2. Now, does it amount to stretching the signal in time or compressing? As usual, I will always have two different answers. What do you think? Sure? How do you figure that out? Suppose I were to ask you this simple question. How do you figure that out? Think of this as, assign this to some x tilde of k, okay. Call this as x tilde of k, this new signal as x tilde of k. Will x tilde look like a bloated version of xk or a compressed version of xk?
Because x1 is equivalent to x tilde s.
Sorry?
x1 is equivalent to x tilde s. So if s is greater than 1, that means the signal is stretched.
Correct. So, you can look at it this way, right? X tilde you are looking at k here, x tilde at 1 would be, suppose s is 2, x tilde at 1 would be what x is at half, right, and x tilde at 2 would be what is x at 1. So, which means you are really stretching the signal now by a factor of 2. So, all values of s greater than 1 will result in stretching of the signal, we call this as a dilation. And what about, obviously now values of s less than 1 will result in compression. Of course, s equals 1 is your original signal. Now you should understand what happens in the Fourier domain, in the frequency domain. Because we said when s is greater than 2, when s greater than 1 sorry, results in dilation of x, you should expect the Fourier transform to compress, right. And let me show you by an illustration here. So, on the top you have some signal, okay, that is your x, and on the right hand side I am showing the you can say the Fourier transform, or you can even think of it as a magnitude of Fourier transform. Now, I am showing you what happens when you scale, right. So, on the left hand side you have the signal shown for s equals 0.5, and it confirms what we just discussed. For values of s less than 1, you generate compressed versions of the signal, and that is what you see here. Here is your original signal on the top, and on the left bottom you see the signal when s is 0.5, which is a compressed version. What has happened to the Fourier transform? It has stretched. Not only has it stretched, something else has happened. The center frequency has shifted to the right. It makes sense. On the other hand, if I dilate the signal, the Fourier transform has actually become narrower, that is let me say the energy spread has become narrower, and the center frequency has shifted to the left. This is a very beautiful and fundamental result which is used in wavelet transforms. The entire theory of wavelet transforms rests on this single property. What it says is, imagine for example the top signal to be the impulse response of some filter, okay. Let us say it is impulse response of some filter, and therefore its Fourier transform is a frequency response function. It explains the filtering characteristics. And what kind of a filter would be the top one? That is, if a system has a frequency response like that I have shown on the top, what kind of a filter is it? Okay. It is not low pass, it is not high pass. What is how does the frequency response look like for a low pass filter? It should be necessarily non-zero at low frequencies. At 0 frequency it has to be non-zero, right. This is how the frequency response would look like, frequency response function would look like for a low pass filter. This is your low pass filter, right. On the other hand, I don't know, here. For a high pass filter, the frequency response would look like this, and for a band pass filter you would see something like what you see on the screen, like a notch. I mean, you can have band reject also, okay. So, band pass filters, so this is a typical band pass filter, that is what you would see. So, what you see on the top, if you were to imagine the blue one to be the impulse response of a filter, then it has the characteristics of a band pass filter, very good. Now, what this result tells me is, all I have to do is, if I want to generate another band pass filter which focuses on the lower frequencies, what do I have to do? I have to design a filter whose impulse response is simply the dilated version of this filter at the top. And the left hand side figure tells me that if I want a band pass filter with center frequency shifted to the right, all I have to do is design a filter which has a compressed version of the impulse response of the original filter. In fact, in wavelet transforms, that is why I call this as a Morlet wave. This is one of the waves or wavelets that is widely used in wavelet transforms. On the top, what you have is known as the Morlet mother wave. Okay. So, everywhere mothers are worshipped, which is great. So, here what you have on the bottom are the children. They are born by simply scaling, right. So, the left one at the top can say, mother, you look fatter than me in time domain, right, because children do say this these days. But then the mother can respond saying, in the frequency domain I am slimmer. Okay. All right. See, it all depends on which domain you are looking at. Likewise, you know, the mother can tell the other dilated version, don't worry child, you may be fat in this domain, but you are much slimmer than any of the other things in the frequency domain, right. So, there is always this trade off now, and this is what is as I said, the central property on which the wavelet transforms rest. Using this simple slide, really you can understand how wavelet transforms are used. Essentially, you can think of wavelets as functions or filters. Even in Fourier transforms, you can think of the Fourier transform as a decomposition of the signal onto sinusoidal functions, space of sinusoidal functions, or you can think of it as a filtering. What you are doing is, you are taking the signal and passing it through a filter. This is not the Fourier atom. How would the Fourier atom look like? It is a sine wave. And how would its frequency response look like? A peak, right. So, Fourier transform in a sense is like filtering. What you are doing is, you have a filter which has a very fine bandwidth, and it is just extracting in theory that frequency component for you. Okay. So, that is a good perspective to have as well. Think of always transforms as filters. You can also think of transforms as approximations and so on, as projections and so on. Anyway, so hopefully you enjoyed this scaling property here, and for those of you working or plan to work in wavelets, hopefully this has done some ice breaking for you.